Thank you for the intro. I am unfortunately not Mohammed Usman Tariq. No, it's all good, it's all good. He couldn't make it. I'm Shiv Sundram. I'm a fourth-year doctoral student at Stanford, and today I'll be talking about tiling recurrence equations. So this is work I did with Kjolstad, my advisor, and it was led by Mohammed Usman Tariq. He couldn't make it due to some unforeseen engagements, but I want to be clear that this is all his creativity. I also want to be clear that he is young, he is brilliant, and he is applying to PhDs this fall, so please look out for his application. So as I said earlier today, we are talking about recurrence equations and linear solvers. A linear solver is just a set of recurrences like the Cholesky decomposition shown here. It solves a matrix system AX equals B, particularly when A is symmetric. Now when A is not symmetric, you can use a different algorithm, the LU decomposition, with the recurrences shown here. And if your matrix is triangular, you can use a triangular solver, either with multiple right-hand sides or a singular one. If you want to solve it through inversion, you can use a TR-TRI, recurrences shown here. And these are all just sort of the code names that the linear algebra community likes to use for these fancy linear algebra routines. And they all have a similar syntactic structure. It's similar to the matrix multiply equation, which I show here to the right, in that they include 2D index tensors, summations, and element-wise operations over matrices. And if we look at it, we'll notice that there are similarities, deep similarities between linear solvers and matrix multiplies. The most fundamental one is that they're both compute-bound. They require a lot of flops. Most solvers are accordingly O of n cubed, just like a matrix multiply. They benefit from cache tiling and register tiling and writing stuff in handwritten assembly. But there are also some very fundamental differences between the matrix multiply and the solvers. So first of all, there are no output dependencies in a matrix multiply. You can see over here that to calculate Cij, you can calculate all of the elements independently. So there is a sort of embarrassing parallelism to them all. This is not the case in a direct linear solver, which is a recurrence. In a recurrence, like the one shown here, future outputs depend on previously calculated inputs. You can see over here that Ri depends on Ri minus 1. That means the outputs have dependencies, and that limits the parallelism. Another fundamental difference, the one we're most interested in, is how these algorithms get tiled. When we tile a matrix multiply, the tiles are identical. What do I mean by that? If I take this output matrix here, decide to tile it up, every small tile is basically just going to run a smaller matrix multiply, which means all tiles are really just smaller versions of the larger operation we are trying to execute. But this is not the case in a linear solver. When I tile a Cholesky decomposition, for example, we end up having to calculate this blue tile and this green tile separately. And as you can see, the blue and green tiles have different shapes. One's a triangle, one's a rectangle. And calculating them requires different operations, which I've shown to the right in those funny code names again, SYRK, POTRF, gem, that's a matrix multiply, and a triangular solve. I'll talk about those later. These tiles are different, so optimizing these are actually just much, much harder than optimizing a plain matrix multiply. So how do we execute these solvers in the real world? Well, the easy answer is just use a library. You can use BLAS or LAPACK. We've had these since the beginning of time. They're really well optimized. So they'll get you the performance you want. But if you're stuck in the case where you have a direct linear solver, some fused or composite version, and nobody implemented it or put it in BLAS or LAPACK, you're kind of screwed because it just doesn't exist and you'll have to implement it on your own. Alternatively, if we want generality, we could use a recurrence compiler. So the user would just input the equations, we would compile them to C code or something, and that'll give us some nice generality, and in, say, sparse cases, we'll get handwritten performance. But for something really dense and tiled, we're just not going to be able to beat the handwritten assembly that's been written over 50 years. Now, ideally, we want a solution that gives us both, right? We want the generality of a recurrence compiler, and we want the performance of a library, and we want to interpolate between the two. So how can we do that? If we take a recurrence compiler, introduce tiling optimizations, and then build a system where we can execute certain expensive but commonly found tiles with the library function, we can get both the generality that we want and the performance. So we built a system called REPTILE, short for recurrences plus tiling, which takes in an arbitrary set of user-provided recurrences, tiles them up, associates any tiles with available library functions, and then emits code with performance that matches or outperforms state-of-the-art libraries, in our case, MKL. We'll use the same Cholesky decomposition as before as our motivating example. And as I said, the blue and green tiles implement completely different operations. They're not matmols, they're something else. Once we tile the algorithm, and this only happens in the tiled case, like other linear solvers, the Cholesky decomposition is going to exhibit a recursive call stack. We see that when tiled, Cholesky simplifies into 4 subtiles right here. There's a recursive call to the Cholesky decomposition, potrif is the code name, a symmetric ranked update, a triangular solve, and a matrix multiply. That's just your gem. And the cool thing is that each one of these is associated with a recurrence. So there's the input recurrence for Cholesky, of course, and the recursive call is going to have the exact same equation, but then each one of these other 3 tiles have equations associated with them too. And the main thing I want you to take away is that these equations are all completely different, right? So you can't just do some recursive tiling, you have to do something a little bit more sophisticated than that. We want to discover, what we want our compiler to do is discover what these subrecurrences are, associate them with tiles in a library, and then just generate the code. The other interesting thing is that all of these tiles are actually hierarchical. So we can do more than just unroll the recursion down one level. The TRSM, the circ, and the gem are all hierarchical operations. So in this case, we can decompose the TRSM, the triangular solve, into a gem and a smaller triangular solve. At that point, we want our compiler to either take these tiles, the leaf tiles, and execute them with a library call. Or if the tile is very small or a good library kernel doesn't exist, or the overhead of invoking a library via a function doesn't really justify the performance benefits, we want to take the compiler approach and generate explicit loops. So in REPTILE, our compiler, that's pretty much what we do. The user is going to provide 3 things. The first is a list of recurrences expressed in a mathematical syntax. Very easy to describe. The second is going to be information about our tiling strategy. Which dimensions do we want to tile over, right? The size of our tiles, et cetera. And then the third is more interesting. It's actually a repository, a sort of bank, if you will, of library functions, which are decorated with their associated recurrences. And this is going to let us compile individual tiles of recurrences into tiles of library calls. We're going to generate each tile, deduce what its associated recurrence is, shown in the middle, and then we're going to lower each tile one at a time to generated loops or a library call. So how does this compiler actually work at the equational level? I'll walk through an example of how REPTILE would do this for a Cholesky decomposition, as I've shown kind of before, same triangle. I've shown one version of Cholesky to the left. The main takeaway is that it's a triply nested loop, right? So it has a 3D iteration space, which I'm just going to visualize with the cube to the right. So each tile is also going to be 3D, so it'll just be smaller. So I'll represent every tile with just a smaller version of that cube. So there's the global iteration space, and here's just the subspace of that. And what we want to do is essentially intersect this abstract representation of our solver, of our recurrence, of our Cholesky, with this 3D tile. And if I do it for this one specific tile here, I'll just choose a random one out of the bag. What I'm going to get is the symmetric ranked K update. It's a mouthful. Of course, this, in theory, should be done by analysis of loops in old compilers. That's how we used to do it. But for very arbitrary inputs and loops, that's just not a very easy problem to do. These things get very complicated very fast. We'll instead show that if we have the corresponding equations, that's all we need. We don't need to reason about loops at all. It's just the user can give the equations, we can analyze the equations, and then just go straight to loops after that. No other program analysis is needed. And we generally think it's a good idea to do this, right? To sidestep difficult analysis programs and just reason on a higher level, more mathematical representation. So instead of this code, I'm going to instead take these recurrences and intersect it with the bounds. So what does it actually mean to intersect equations with bounds? Well, I'm going to take this cube right here and replace it with the inequalities that represent that subtile. There's 3 of them because it's a 3-dimensional iteration space tile. And then when I intersect them, something really interesting happens. The outer expression for this very specific tile, those who are mathematically inclined may realize what's happening. The outer expression just disappears. For this specific tile, it doesn't matter. It's never going to execute. We're left with these sub-equations right here. And this is the exact equation that we see in the symmetric ranked update. So I'll walk through that a bit more step by step to kind of intuitively explain why this outer expression is just disappearing when I intersect with this tile. So imagine we have this equation here. For the sake of simplicity, I'll remove the subtraction. So then all we're left with is a summation and a square root on top of it. Let's say it's just 8 elements. And I want my first tile in blue over here to execute the first half of the summation. And our second tile will implement the second half of the summation in green. It'll finish up the accumulation. Now, once we finish those 2 half summations, what we can't do is what I've just shown on the screen right here. We can't take the square root of each and then add them together. Why? Well, simple mathematics. Square roots don't distribute. They can't distribute over the inner summation, so it's not going to work. And that's sort of why the tiles all have to be different. What you have to do is take the first tile, and that's free to do the summation, as before. Have the second tile, which comes after, finish the second half of the summation. And then you can have the second tile execute the terminal square root, which it can do because the second tile just finished the entire accumulation. So that sum is essentially ready to be executed. So you have one tile that's just doing summations or multiplications, and then you have a second tile which is doing the same thing for the second half, but then doing the square root on top. And the result is that the first half and the second half are different tiles, and they simplify to different recurrences shown here. We do this for every abstract tile, and that lets us discover this recursive call stack that I showed before with lots of different equations at every level of the hierarchy. So what I showed you was the intuition behind our core algorithm, and for the details on how we generated the candidate tiles, how the intersections are implemented in the weeds, how we handle dependencies, please see the paper. So to go to our evaluation, we evaluated our REPTILE generated code against MKL for the Cholesky, LU, and triangular solves, and we got 1.4x speedup. Now, the ironic and kind of funny part about this is that we're evaluating against MKL as our baseline, but when we linked to external functions for our individual tiles, we linked to MKL calls as well. So we got better performance by MKL, but by using the library against itself and simply discovering a better schedule. So basically just 1.4x speedup, 1.1 to 1.4 for all the major solvers. For less commonly used solvers that you don't see in the wild, we notice we got up to 2.7x, and that makes sense because they don't get optimized as well as, say, a matrix multiply. We did compare against the matrix multiply, and we got no speedup whatsoever, which makes sense because artificial intelligence and yeah. And then we also evaluated this against some non-solver recurrences just to show it's possible. So in this case, we have some bioinformatics algorithms, and we were able to get about 1.6x speedup over the handwritten baselines. Yeah, so once again, I am not Usman Tariq. This is Usman Tariq. He's taking this to some pretty ambitious directions, and of course, he is applying to graduate school this fall. And we do believe that this path gives us, this work gives us a path to portability over architectures for direct linear solvers. We're looking at compilations to GPUs, to supercomputers, and generating custom spatial architectures from the recurrences themselves. And that's it.
Hi, Shiv, great talk. I was wondering, since you're using SMT to solve the intersections, are all the terms generated for these kernels affine? And if they are, do you foresee any useful programs in the future that would generate undecidable intersections?
Right, so we don't imagine running into problems there. There's a lot of interesting problems like Floyd-Warshall, which aren't exactly affine, they're like pseudo-affine. We could perhaps run into problems there. We actually simply used SMT because the interface is just so clean and it's really highly optimized. The correct thing to use, from a purist point of view would have been integer set library or something like that to do integer set intersections. So I don't foresee anything for solvers. For pseudo-solvers, like Floyd-Warshall or graph problems, maybe I'd have to look into that.
Gotcha. Thank you.
Yeah.